Okay, welcome back. I guess I accidentally stopped recording in the last video. So I wanted to make that video again. Here we've got our hyperbolic sine function. We know that that is 1/2 e to the x minus 1/2 e to the negative x. So the graph gets very, very close to these two curves, 1/2 e to the x and 1/2 e to the negative x. We see that as x goes to infinity, the y values go to infinity. As x goes to negative infinity, the y values go to negative infinity. But again, they're approaching these two curves. And then at 0, the hyperbolic sine of 0 is 0. Now, if we look at the tangent lines to that graph at particular locations, we see that the slope is a +1 here. And then as x goes to negative infinity, we see those slopes are just getting more and more positive. So we start all the way out at negative infinity. The slopes are very, very large. And then the slopes are still positive. If we just look at the tangent line, then we look at rise over run, the change in y over change in x, they're always positive numbers. And then at 0, we get that slope of 1. And then they start getting steeper again. And the slopes just increase and increase and increase. So we would imagine that since the graph has slope or tangent lines that always have a positive slope, that its derivative would always have positive values. And it turns out that that's the case. When we did the computation by hand, we found that the derivative of hyperbolic sine was hyperbolic cosine, and hyperbolic cosine looks like this. The range of hyperbolic cosine is 1 to infinity, and we see that when we are at sort of large negative x values, the magnitude of that slope is very, very large. The line is very steep, and so we're going to have very large y values for our cosine or our hyperbolic cosine curve, because the y values on this curve are giving us the slopes of this curve. And then as x gets closer to 0, we see that those slopes decrease until they get to 1. And then from 1 to infinity, the slopes increase again. So it's from positive to less positive to 1, then to positive again. That's very consistent with what we might expect. Now we can also change our sort of frame of reference. And instead of thinking of sine as the curve and cosine as its derivative, we can think of cosine as the curve of interest and think of sine as its derivative. So let's draw some tangent lines on the cosine graph now. If we move that slider, we can look at the tangent lines at various locations on the curve. So there at the bottom, the slope of the tangent line is 0. Now, as we move our tangent line to the left, so our x naught goes to the left, we see that the lines get steeper, but they all have negative slope. The line falls as we look at it from left to right. So the corresponding slope should be negative numbers, and then the farther we get from x equals 0, the larger in magnitude those negative numbers become. So if we want to see the actual slope at different locations, we could just calculate rise over run. It looks like at x equals negative 3.12, the y value for the hyperbolic cosine is 11.345, and the corresponding slope is negative 11.3. But you can change that. You can let the x values change. You can see that the curve is less steep here, so the magnitude of the derivative is less in general. Here, according to this, the slope is -3, approximately -2.94. But so we have that as our negative slope, but and we can calculate that by just looking at the grid, doing rise over run or fall over run. using that to calculate a slope. But then again, as x goes to 0, those slopes go from being negative on this side to being 0 here, and then the slopes on the right of x equals 0 are all positive. So we start increasing, and now the slopes get larger and larger as the line gets steeper and steeper. And that's consistent with the function values for the hyperbolic sine of x. The derivative of the hyperbolic cosine is hyperbolic sine, so the values of the hyperbolic sine give us the slope of the secant line of the hyperbolic cosine. So that's that. Just wanted to demonstrate that for you. In another video, we'll look at the hyperbolic tangent function and its derivative, and then we'll derive the formulas for the hyperbolic secant, hyperbolic cosecant, and hyperbolic cotangent functions.